So Lab 5 is about experiment management. It introduces the IAM dataset of real handwritten lines. We're going to take a look at that dataset and then make our synthetic dataset look more like it with adding data augmentations. We're going to introduce weights and biases for experiment tracking. And we're going to run some experiments on these updated EMNISTlines. And we're going to kind of show how to use weights and biases as we run experiments. And lastly, we're going to start a hyperparameter sweep. To follow along, you can just git pull, make sure you get the latest version of this repo, go into Lab 5. If you're doing this on Colab, there's a couple of new packages that we need in this lab, namely weights and biases and bolt-ons. So just make sure to install them in addition to the usual thing that you do in setup. So the first thing I want to talk about is this new dataset called IAM. It's a dataset of real handwriting gathered by, I'm not sure whom, but at some point, probably in the 90s or the early 2000s. And we can take a look at what it looks like by looking at a notebook. But before we look at a notebook, I actually want to look at the raw data. So when you first, check out the repo, you just have the raw data about IAM, right? There's a README about it. It describes the data set. This is good practice, by the way, to do. Just have a README with every data source that you have, describing, if you did any pre-processing, how it should be split, where it's from, the provenance of the data. So this one is about 1,500 pages of scanned text, separated out into 13,000 lines of text. There's metadata that has the URL from which we can download the data, a hash for it to make sure that we downloaded the right file, and then also the IDs of pages that should belong to the test set. And this is important if we want to compare our numbers against published numbers, because this is the data set that was kind of published alongside the images. So once you actually run, so for example, you can run Python text recognizer data IAMLines.py. So if you run that, it will download the data set and then do some processing. So let's just wait for it to do that. Or I can actually switch to one where it's already downloaded while we wait. So it'll download it into this data downloaded folder, and also, well, I guess it's not downloaded here. So let's just look. Yeah, so in the downloaded folder, we have IAM. So forms has the raw images, and we can just take a look at what they look like. So this is what type of data people provided, right? They were told to take a sheet of paper like this and then write out in their own handwriting the text up here. And then the data annotation was annotators went through and drew basically line rectangles around each line, and in fact around each word. And so now we have the locations and contents of every word and line in this data set. So we're going to use that and compose a data set of lines. So I'm switching to the notebook now. It's 03 look at IAMLines. We're going to pass augment data to false just so that we don't see that just yet. It loads it. The dimensions are 56 pixels high by 1024 pixels long. The max sequence length is 89 characters. And we can look at what it looks like by just plotting them and then putting the label as the title of each figure. You'll notice that each starts with a start token, ends with an end token, and I'm stripping out the padding tokens. So each one of these is padded to the max length of 89 also. I'm just not showing that. And then the images kind of look like this. So there's a diversity of handwritings. Some of them are kind of compressed horizontally. Some of them are slanted. Some of them are kind of maybe rotated, like there's a slant to the overall direction of the line. And the goal of looking at the data is just to see what might be out there. We're also plotting the data between 0 and 1. So then black is 0, a pure white would be 1. And so we're seeing that most of the actual ink is kind of maybe at 0.7, 0.8 or something like that. It's not pure white. So now that we've seen this, we can try to make our own synthetic data set look more like it. And so we have that EMNISTLines dataset that we composed, and we can actually look at that in notebook 02. And it's good practice to number your notebooks. So if you remember, we had some simple strings like that, and then we had slightly more complicated ones like this, where we introduced some character overlap and just longer sequences. But they were all pretty simple in that the text filled the whole vertical space of the line. It always started, right on the left edge, and it was all on the same kind of horizontal dimension. It wasn't like ever stretched or slanted or rotated in any way. So to make this look more like this, we're going to need to introduce some extra things. And so for that purpose, we made this EMNISTLines 2 dataset. It's mostly the same code as EMNISTLines, but it now looks like this. So there's rotation, there's less, it's less pure white, and it's more faded at times. It's horizontally compressed. There's a slant to some of them. The slant can be in both ways, and it can start not just at the beginning of the line, but anywhere in the image. So this is much more realistic, and we can also look. So this is the training set, and we can also look at the test set and see that it's still kind of the old version of it. So I want to show really briefly code that can make that possible. So if we open up EMNISTLines 2, the key piece of code is the transform that we pass to the data set. Okay, so to make the train and the validation set, we pass this transform, the result of a function called getTransform with augment, which is going to be equal to true. And so what are transforms? So this is known as data augmentation, and we have been using a transform that just changed anything, NumPy array or a PIL image to a torch tensor. So we use this transforms to tensor transform function. But now we're also going to, if augment is true, we're going to jitter the color. So we're going to vary the brightness of the image between making it half as bright to remaining as is. And we're going to add a random affine transform. Now what is this? So we can always search for torch vision random affine and then see what that's about. So basically we're able to rotate the image, translate it vertically and horizontally, scale it around the center point, shear it, which refers to kind of adding this handwriting slant, and also, well, I guess, those 4 transformations is what we're actually doing. So we do a little bit of each one of them. And the beauty of it is that it's random. So each time a batch is loaded, a different random transform is applied to the images. So that's really going to be key to preventing overfitting, as Josh explained. So this is what our data looks like. And we don't apply that data augmentation to test, which is why test still looks like this. And we could apply the data augmentation to test in this case, but it's usually good practice to leave the test set kind of untouched by any data augmentation so that it's always the exact same performance number every time you run on the test set. It doesn't actually depend on anything random. So that is EMNISTLines. So now we're ready to run some experiments, and this time we're going to be keeping track of them using weights and biases. If you don't remember, it's one of the experiment management tools that we covered in the infrastructure lecture, alongside Comet, ML, for example, or ML Flow, or Determine.ai. You know, there's a bunch of examples of this basic idea. I like weights and biases. It's fast, it kind of has all the features, and it has some more advanced features such as hyperparameter sweeps, which we'll use in this lab also. So I think it's worth getting to know weights and biases. To set it up, okay, let's say you're running on Colab. So the first thing you'll do is you'll run WNB init, and that'll pop up and a message that says, okay, let's set up this directory, please paste your API key. And then it'll send you to WNB.ai authorize. And when you get there, of course, you're not signed up for it. So you'll have to either log in via GitHub, which I think is easiest to do, or Google, or sign up for an account. The account's free. This functionality is all free. So feel free to just sign up for it or just log in with GitHub. And then go to settings. And then you'll have an API key down here, which you'll be able to copy and then paste into your Colab. And that will set up your repository, or that directory, with WNB. And the next thing it'll ask you to do is enter the name of the project. And you can type really anything, but you might as well type the name of this repo, which is FSTL Text Recognizer 2021 Labs. Okay, so now we're logged into WNB and we're set up our directory with it. So what is the actual code that we should add, or has been added for us, that's going to use WNB for logging? So that new code is in runexperiment.py. So let's take a look at that. So remember, runexperiment.py is our framework. It reads, stuff from the command line. It loads our data, our model, and our lit model. And now we can pass a command line flag --WNB. And if we do that, it will replace the default TensorBoard logger with the WNB logger. And this is literally the only change that happens in order to use WNB. So that's quite nice. We simply replace the logger, and then we additionally, and this is actually optional, but we have the logger watch the model, which will actually keep track of all the gradients and be able to plot all the gradients, the magnitudes of all the gradients in our model on WNB. And we're also going to log all the hyperparameters. And for us, all the hyperparameters are everything that's on the command line, right? So that's in order to change some kind of thing in our code. If we want to be able to search over different values of it, we make it a command line argument, and then we call all of our command line arguments hyperparameters. So this is the extent of the integration. It's quite nice. The next thing we want to do is just to be able to run an experiment. So let's take this command, which is Python run experiment with this new WNB flag. We can just run for a few epochs at first on this new data class that we have, EMNISTLines 2, with our old friend lineCNN transformer and the transformer loss, which will use the transformer lit model. So if we take that and we paste it into our terminal or into our Colab, remember to precede it with an exclamation mark, then what we'll see is just the standard kind of beginning of training view. We'll print the model and so on. Except now, at first, it'll say WNB, we're currently logged in, and it'll link us to this project and this specific run. So we can open this. And be able to see the config, so all the hyperparameters, like for example, comp dimension, right? Everything that we ran with, if we overwrote something on the command line, it would show up in this config. The charts, which will show up pretty soon as we get through our first epoch. And then lastly, this media, which I'll talk about in a second. So, okay, so the first epoch is now completed. So we have one data point for the training loss, the validation character error rate, and the epoch. One thing I like to do is change this epoch chart to be based on relative wall time. So that's nice for comparing multiple runs, is like how long is each run actually taking. And then the training loss, instead of in terms of number of steps, which is another word for batches, I think it's a little nicer to see it in terms of number of epochs. Same for the validation loss. Same for the character error rate. And then maybe I just want to arrange them a tiny bit differently. So I want to see training loss next to validation loss. So I said we're logging the gradient magnitudes for all of the layers in our model. And that's kind of cool. So we can see the brief distribution of gradient magnitudes. And what this can let you see is gradient explosion. And so there you would see, instead of like a blue, thin line, everything would be kind of uniformly colored. Or gradient vanishing, in which case, everything would be set to basically straight zero and there would be no distribution of magnitudes around it. Okay, so now we're training. I'm going to switch to something that is already, I think it's finished. It's been running for a while. And so this is kind of what it can look like. And we can see if there's multiple runs. So yeah, so in this particular project, I had 3 runs. And one of them I just launched. It's running right now. That's why it has this green dot next to it. This one ran and finished, and then this one ran and finished. And we can compare them, which is really helpful. We can see the final test character error rate. And this is kind of cool. I want to talk about this media. So if we click into this experiment that's running right now, you see something that's called validation pred example. Okay, and then the image is so that by, and the prediction is this there and the at. So that's not quite that nice. But where's this coming from? So this is coming from the transformer lit model. In lab 5 has, in the validation step and the test step, now has this little bit of code, which is, we make the prediction on our batch here, and then for the first element of that batch, we're going to actually turn that prediction into a string that we can read, and then log it using the WNB logger as a val pred example. And this WNB.image is really helpful because that's what is able to log that rich media. And there's support in WNB for audio also, and for different other types of, just different formats of data. So as you can see, this is really not, this says something truly amazing, and the prediction is still the sum, the sold, the. So it's really just garbage, but interestingly, it's English language garbage, right? So what that's telling us is that in this short time, we've actually, the transformer part of our model has actually learned how to produce text, but it hasn't yet learned to actually understand the image just yet. It's pretty remarkable that it's able to produce any kind of text though. If we look at something that's been trained already, let's look at the other runs here. So this orange one, Vital Valley 2, this one gets 4% test character error rate. So let's click into that. Yeah, really nice, training loss going down pretty low. Same with validation loss. So let's see what it actually produces as a validation prediction example. So the image is something truly amazing, and the prediction is something truly amazing, which is pretty cool. And we can step through training. So this is a mistake here. I read for a few moments but the model read for a few minutes and. So, but it's pretty cool because you can actually go back in time and see how the model is getting better as it trains. And then of course, after the testing set, the test evaluation run completes, we get the test pred examples as well. So, last thing I want to talk about in weights and biases, experiment management. This is a cool view, right? Because you can compare curves, but this table view is also quite cool because you can add notes. And so in this table view, the first thing to do is click this automatically show the most useful columns button, which will most of the time show like all the things that are different between the runs. And in this case, actually, none of the hyperparameters are different, but we can introduce them manually by just dragging from hidden to visible columns. And then we can see what the hyperparameters are. And this notes thing is really helpful because as you do your experiments, right? Let's say first you sort by the creation date. So this is the latest one. And so maybe something's different about this run that you're trying to understand. So you can add a note and say, trying precision equals 16, right? And that'll be a note for yourself that lets you see what you're actually doing. And that's quite helpful if you actually have a real project going, because oftentimes you're changing the hyperparameters on the command line, but you're also changing the code. And it's those code changes that are really hard to track down later. So adding a little note and maybe even doing a git commit, that's going to be really key for knowing what the heck you did, tomorrow. Trying precision 16, that is one thing we can do now. And we've actually been able to do it for a while, but on the command line, if you just type precision equals 16, it'll run the same experiment in mixed precision mode using native PyTorch 16-bit support. So this can really speed up your experiments by lowering your memory footprint. So if you do precision 16, you can now increase your batch size. Our default is 128, but we can try increasing it to 256. So this is basically always worth leaving on as a default flag, precision equals 16. So the last thing I want to talk about is, so we ran our first W&B experiment. So now let's say we got to a point where we're pretty happy with our experiment. Like maybe we got something to converge, but maybe it took a long time, right? Or maybe it's not quite converged, but it feels like we're pretty close. Like if we just changed maybe the learning rate or the number of layers, it could actually converge. And so that's a good time for a hyperparameter search. Now we've set you up with one sweep, which is the word that Weights and Biases uses for these hyperparameter optimization experiments. So let's go ahead and take a look at training sweep. Okay, so it's EMNISTLines 2 line CNN transformer.yaml. So the important thing is we specify the program that we want to run, training run experiment, the hyperparameter optimization method, which can be one of three things. It could be grid, it could be random, it could be Bayes. So Josh talked about all of those. Let's go with random for now. The metric that we want to optimize. So in this case, we want to minimize the validation loss. This is a really cool feature called early termination using the hyperband algorithm. So what it will do is if within the first, in this case, 20 epochs, an experiment is not better than an experiment that already exists, then we can actually just terminate that experiment. So this is something you should watch out for, because let's say if you use a lower learning rate, you might have got to a point in 20 epochs with a higher learning rate than in 60 epochs with a slower learning rate. So it's good to be conservative here. So maybe go with like 60 epochs for this early termination. And then the list of parameters that we want to pass to the model. And if you don't want to change the parameter, you can just exclude it. Or just if you want to remember what it is, you can just give it a singular value, like Windows Stride 8. But if you want to range over different values, you can give it as a list, or you can, if it's a float parameter, for example, like a learning rate, we could do min 0.0001, max 0.1, and then it would randomly sample. But of course, we want to include that 3e to the -4 learning rate, so we'll give it manually. And in general, I think it's, I don't know, for the stuff we're doing, it's worth just typing that out just so that you can kind of see everything that's going to be tried. Okay, so we're going to do 16-bit precision training, line CNN transformer, EMNISTLines dataset, and then we're going to randomly sample a setting of all of these parameters, right? To launch this sweep, we will type WNB sweep, and then a path to the sweep, which is training sweeps, EMNISTLines. So if I just run that, it will contact the WNB server and set the server up with a sweep, basically point that our agents can now call into and ask for a set of parameters. So the next step is we have to launch an agent. I have 2 GPUs on this machine, and there's a thing I like to do, which is using this CUDA visible devices flag, or environmental variable. I can only expose one GPU to the process I'm about to run. So I'll run one agent on GPU 0, and then get another terminal going. Expose the second GPU and launch another agent. So now I have 2 WNB agents, and each one is calling into WNB to get a set of parameters and then starting its run. And all of these runs are going to show up at that URL that I was shown when I started the sweep. So view sweep at right here. Can't seem to click on it, so let's just navigate to it. Go down here to sweeps. So here's the sweep it's running. I have 2 runs, well, I have 4 runs going. I don't know what's going on there. I should have 2 runs going. Maybe I accidentally launched them twice or something. But in any case, we have multiple agents running sweeps now, and they will all show up in this place. And a cool thing is this kind of view where as your runs complete, they will terminate onto the metric you care about, which maybe is validation loss or maybe validation character error rate. And we want it to be low, of course. So we can see like what is the setting of all these parameters that we care about that's leading to the lowest loss. Let me think if I'm missing anything. You can do this in Colab too, which is actually pretty cool. So I created the sweep in Colab and I ran the agent in Colab. And it's happily running. Yeah, and this one's down to 6% validation error. I think that's pretty much it. The thing to try in your, in the next week, definitely try to run at least one experiment, logging to weights and biases. And the homework is to actually just upload a screenshot of your weights and biases kind of table of runs. You can try to find a setting of hyperparameters for the experiment we're running that maybe trains fastest while still reaching a low CER. See, these ones are, I want to get out of the sweep view. 1 second. So these runs that we ran, They get to a low character error rate, but it takes a while, right? So if we flip to time here, it maybe takes, something like 30 minutes to crack 10% or so. I think you can actually do that in like 10 minutes. We just have to find the right settings. And in this case, it'll be reducing the number of parameters here. So maybe fewer transformer layers or a smaller conf dimension. And you can try experimenting with line CNN LSTM instead of line CNN transformer if you want. You can try to run on IAMLines. You can try running a sweep and pretty much anything you want to do. But just get comfortable with logging to weights and biases.